run your. So we'll wait for a couple of minutes. You guys set it up, and then I'll start explaining and executing the code. Okay, I hope everyone has made a copy of the collab notebook. Let me share my screen. Shifali, am I audible?
You're audible.
Okay. Okay, let me share my screen.
Yeah. If you want, you can wait two more minutes.
Yeah. My screen is being shared, right? Can anyone confirm?
Yes.
Okay. Fine. So I think I made some changes to this notebook, and probably I haven't shared the updated one. So I'll do one thing. Let me share this. So as some more content that I've added. Okay, I request everyone, you please open this one. It has some updated content. There's a lot of notebooks opened here. Let me close some. Everyone, please open this latest link that I've shared. It has the updated notebooks content. Okay, I hope everyone is ready then. So let's jump into it. So today we'll look into something known as word embeddings, right? And what do you mean by word embeddings? Why word embeddings are needed? And what are the different methods of creating word embeddings? So we will look into a couple of methods, and if time permits, maybe we'll look at a different method also. Let's see. But yeah, so last class, I remember, last to last lab session, I remember which I took. It was all about neural networks and how do you create neural networks, right? But at that point in time, we only saw how to deal with numbers. You have a set of numbers, and then you can input those numbers to the neural network. You can train the network, and maybe want to predict something out of those input numbers, right? But we haven't yet seen how to handle text, right, with neural networks. And why handling text is necessary, because the world around us uh, is text heavy, right? We humans communicate with text. We deal with text very often, right? So handling text and making models that can handle text is extremely essential. And you also see nowadays, you deal with all these LLMs, right? You deal all with ChatGPT, Gemini, and everything. And you input a text, they process it, and they give you output in text, right? So understanding how a model handles text is utmost essential to understanding these things, right? So now, when I say word embeddings, what I mean is every word. Uh, so let us recap something, right? So earlier in the last to last lab session, we saw that if you have a set of numbers, right, you can represent that number with a vector, right? And then that vector can be sort of given as input to the neural network, and then you do all sort of weight multiplication and soft activation for applying non-linearity. And then at last you can apply a softmax layer to basically find out a probability distribution of what is your target output class, right? I hope this is clear to everyone, right? uh, so now one thing is very essential in this entire discussion, is that neural networks can only handle numeric values, right? Because when you do matrix multiplication and all those things, right, you can't have words in them, right? Anyway, you have to deal with numbers. So the idea of embedding for a word is basically how do you represent a particular word in the form of a number. And when I say number, I mean a vector, right? So it's like every word in a particular vocabulary, right? Let's say you're considering English, right? So every word in a particular language or a vocabulary can be thought of as one point in the embedding space, or a vector space, right? So you can imagine, if you have, let's say, 1 million words, those 1 million words would have certain representation, right, in the vector space, right? So that is the idea of word embedding, right? But before, so I hope the idea of why you need to convert words to numbers is really important, and it is clear to you, right? Um, if that is clear, let us see. Let us first see how we can do this in a very trivial way, right? And why do I say trivial? We'll sort of understand it later. But um, let us see one way of how we can represent words, and probably this is one of the popular ways that people used to do it in a very early stage of NLP, right? Natural language processing. Um, so that particular method is called one hot encoding. What does it mean? So every word in your vocabulary, right? Vocabulary is a collection of words. So every word in your vocabulary can be represented by a vector, right? And those vectors would be a zero, a one hot vector, right? One hot vector means only one position in that vector would be one, and rest all positions would be zero, right? And what does it mean? So let us see. If you have a vocabulary of something like, let's say you have a sentence, right? Learning data science is fun. Uh, let's say we only keep this. Learning data science is fun. What is it? Cool. Okay. So, right. So if you have a sentence like this, learning data science is fun, right? And you want to convert these particular words of this sentence into a vector uh, in a one hot way, how does it look like, right? So you see your vocabulary size is 5 year. Data, fun is learning science, right? So, and the position of these words in this vocabulary is important, right? So this is in first position, this is in second position, this is in third, this is fourth, and this is fifth, right? So if you want to represent each of these words in a one hot way, what you would basically do is convert this into this vector where you would put one, like, and all the positions should be initially zero. You would only put one in the position where the word lies in the vocabulary, right? So this particular word science lies in the last, right? And first, and one more thing to note is you have one, two, three, four, five words, right? So you see your vector size is five. You have five elements in the vector, right? So initially everything is zero. Then we see where is science. So science lies in the last position, right? So last position is one for science, right? Similarly, you see learning, right? Everything is zero initially, but you see learning is in the second last position, right? Or in the fourth position. You see the fourth position is one, right? So this is one way you can represent words in vector form, right? Is this clear to you? So basically, this particular representation is called one hot representation, where for a particular word, the position in which it lies in the dictionary or vocabulary would be one, and rest all positions would be zero, right? And what would be the size of the vector? The size of the vector would be equal to the number of words you have in your vocabulary, right? So you have five words in your vocabulary, your vector size is five. Whichever position a particular word appears in the dictionary or vocabulary, that particular position is one, rest everything is zero, right? So now you see essentially you convert. And also one important thing is uh, these particular words, when you convert to vectors for the neural networks to handle them, has to be unique, right? So you can't have the same representation for data and fun, right? But essentially then that would collapse, right? The meaning of those two words would collapse if you have the same representation for these two words, data and fun, right? So you have to also make sure that when you're creating this representation, each word would have its own unique representation, right? And that is the reason you, based on the position, you set one, and then everything else is zero, right? I hope this is clear. So this is one of the earliest ways, you know, in which people used to create these word embeddings. Then once you have these, once you, for every word you have this vector representation, you can simply put in this vector representation, right? And then you can simply pass in through the neural network, because now it is numbers, right? And we know that neural networks can easily handle numbers, so you can easily pass them through the neural network and do all sort of stuff, right? I hope this is clear to you. So now, having said this, so uh, can anyone point out what can be the downside of this approach? So it's a very trivial approach. So can anyone just point out what can be the downside of this approach? Anyone?
Uh, Sir, data will be very sparse, only 0101. This is the down, disadvantage.
Right. That is one primary disadvantage of this particular approach, right? Because we want uh, things to be, we don't want to waste memory space, because memory is expensive, right? We don't want to waste that. So ultimately, when we convert these, everything is zero. Only one position is unit, right? Everything else is zero. So there's no meaning to kind of store all the zeros in the memory, right? Yeah, that is one downside. Any other downside you guys can think of? I've already written that also. Uh,
Sir, no
size part.
semantic meanings.
What do you mean by semantic meanings?
Uh,
You're
Sir,
correct,
in
though, but
semantic, okay. So, sir, in semantic meanings, these similar words are appear together in the vector space, and yeah, that is.
Okay.
Let's
So
suppose we have two words, good and
yes,
excellent. So they are similar words.
yes,
Like the king and man, they're similar words. So they will be very close.
yeah, right, right. So that is, yeah, that is one problem. Uh, yeah. So these two were the problems that I was also going to talk about. First is sparsity, right? So let's say if you have 50,000 words in your vocabulary, right? So then you imagine the vector size of each word would be 50,000, right? And of those 50,000, 49,000 would be zeros, and only one position would be one, right? So you see, there is a lot of memory wasted on zeros. That is one. Uh, Another point is, uh, it's like you can't have dynamic vocabulary in that sense, because now if a new word comes, uh, you know, let's say your vocabulary initially has 50,000 words, and then a couple of new words come up, right? You can't go and change every 50,000 vector to 50,002 vector, right? So that would be another problem. Second is, these representation do not convey any meaning to us, right? Because if you just like he pointed out, if you have two very similar words, right, the notion of similarity, that apple and orange both are fruits, right? uh, 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 but apple and spaceship, let's say, these two words are not very related, they are very far off, their semantics is quite different, right? But if you consider apple, orange, let's say watermelon, right, their semantics are same because they belong to a class called fruit, right? So that kind of a notion of semantic meaning is not present in this kind of representation, right? So that's why inherently this representation is pretty bad, right? Because of these two reasons. So then, to kind of overcome this limitation, what researchers uh, tried out many techniques, right? One of them, and one of the earliest and most popular technique that they came out, was something called as word to vec, right? And it's a neural network based approach. So basically, what is the idea of word to vec? Word to vec says, uh, word to vec is built upon this concept of distributional semantics, right? What does distributional semantic mean? It means that words that appear in similar contexts should have a similar representation, right? Something. So you can think of something like rain and umbrella, right? More often than not, we will use rain and umbrella, both the words in a same sentence, right? So that essentially means that these two sentences are somehow correlated, right? Am I am I am I able to understand? Uh, am I able to make you understand this concept? If you have any queries, please let me know. Right? So distributional semantics is important because it tells you that if words appear in similar contexts, they should have a similar representation. And why do we care about similar representation, right? Why do we even care about these things? Because we want that the neural network in which we will sort of give these words as inputs should already be somewhat aware of what these words mean in vector space, right? So if I have a similar representation of coffee and tea, then it would be easier for the model to understand what is going on, rather than if I give one hot representation, right? Then there is no relation between these two vectors, right? So we want such a representation where words that appear in similar context have similar representations or similar embeddings, right? So if you see this example here, I often drink coffee in the mornings, right? When I'm thirsty, I drink water. I drink tea before I go to sleep. So you see words like these, like coffee, tea, water. So these tend to have a similar underlying meaning, which is beverage, right? So and these, like tea, water, coffee, tea, coffee, these words, they tend to appear in similar contexts more often than not. So ideally, they should have a representation which are closer in the vector space. And when I say closer, I mean, if you take some kind of a distance measure between them in the vector space, let's say Euclidean distance, or let's say cosine similarity, right? Cosine similarity between two vectors gives you how far apart, what is the angle between them, and sort of things. So you'll see that these two vectors should be close together in space than some other vectors, right? For example, if I compare coffee with, let's say, university, right, or coffee with, let's say, building, those two words should be far off in the vector space, right? That is the idea. And also, let's say words like which stem from one root word, right? For example, drank and then drinking. So these two words should also be close together, right? Swam, swimming. These essentially mean the same, right? But so these should be close together in space. So this is how you can sort of visualize what I mean by words lying in a vector space, right? Let's say if a 3D space, and then what do you mean by words lying in that space? So drank, ideally drinking should be very close here. Swam, swimming should be very close here, right? Then some word, let's say university, which might lie here, or some word such as building, which might lie here, right? This is the idea. So how do these people, and I've also sort of put up some links here from which you can sort of get a conceptual overview. Also the research paper I have attached here, right? So you can also go through them after this session. But yeah, uh, now how do they go about it, right? Now I said that this is a neural network based approach, right? So what neural networks, so that now couple of questions should come to your mind, right? What kind of a neural network are they using to do it, and what is the input, what is the output, what is the loss function or optimization function they're using, right? So the idea is, uh, how do you do it? Let's say you have a large corpus, right? You have a large piece of text. Let's say some Wikipedia document, collection of Wikipedia documents, right? And one more thing, when you want to understand distributional semantics, right, which words appear in context of which words, they should have similar representation. Which words do not appear in context of one another, they should have a very far off representation in space. So if you really want to understand these things, then obviously, as a human, also you need to go through so many texts, right? These relations are already in your mind because you have read so many books, you have read so many blogs on the internet. Uh, so that is how these relations have also stemmed up in your mind, right? So for the neural networks to learn those relations and make representations that sort of put this into factuality, they would also need a lot of data and lot of text to understand those intricacies of the relations, right? Um, so to do that, they sort of, this model would be trained on a large corpus, right? And it would be sort of the once the model is trained, we can get, for each words we can get a vector representation, and those vector representations would hold this property. Which property? That similar word should be closer, right? Dissimilar word should be far off, right? Also, another advantage is then you would have a fixed size vector, let's say 300 size, 400 dimension, 500 dimension. You do not need to change the dimension even if a new word comes up, because we will see that some words can be, the representation of some words can be directly found out using linear extrapolation of some other vectors, right? So it's easier to accommodate new words as well, right? So I'll show you what the basic concept of this paper is. It basically does this learning word representations using two approaches, right? One is SIBO, which is basically continuous bag of words, and another is called skip graph. So what happens in SIBO is, you have the input sentence, right? Uh, it might be an entire sentence, or it might be a part of an input sentence, right? A segment of the sentence, right? And what you basically see here is, so for that sentence, these are the words, right? So WT minus 2 would be a word. Then the next word would be WT minus 1. Then WT would be another word. WT plus 1, WT plus 2, right? Let's say you're dealing with these 5 words. So in SIBO method, what essentially will do is, you will remove this WT word, right? You'll remove this WT word. You will only give input only give us input these context words, right? So when I say WT, this is a center word, right? And I might also sort of, let's say I'll write it here if you can understand it better. Let's say I am learning AI, right? So let's say if learning is my target word, WT, right? Sorry. Then my WT minus 2 would be I, right? WT minus 1 would be M, right? Similarly, WT plus 1 would be AI, right? And just to make it even, maybe I can, well, I think, uh, artificial intelligence, right? So this would be artificial. Right. So the idea is I will give the model as input these context words, right? These are context of learning. So this is learning. So when I say this is the target word, then these words become the context of these words, right? So I will give the model this context, right? And I'll tell the model to predict this word, learning. So if you see, you're giving the context is WT minus 2, T minus 1, T plus 1, T plus 2, and you're trying to find out from the model, you're pushing the model, you are making the model learn that given this context, you should predict this word, right? And this happens over a course of training, and you'd have an objective function and loss function. And we'll see that later. But let us first understand what is the core idea. So basically, when you do this, you're saying that, and how the notion of distributional semantics come here, you're saying that given this distribution of words, right, you should know that this word comes in their context, right? So if something like artificial comes up, you know that artificial intelligence, these two words should be close in space, right? So that is the idea. So essentially what SIBO does is, I will try to maximize this probability of WT given probability of W. For simplicity, let us say the context, right? Now this probability of context would be probability of W T minus 2, T minus 1, T plus 1, T plus 2, right? And since they are IID, which is like independently distributed, so we can simply sort of think of their chain as multiplication of this, right? You know, independent, how to deal with probabilities which are independent in nature, right? So, and if I sort of also try to write that given probability of, right, W T minus 2. So I'm just formalizing it here, right? And comma dot 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 probability of W T plus 2. Right? Makes sense. So basically, you're maximizing this objective where you want the model to predict with maximum probability this WT given this window. Right? So you can think of it, if you give a large enough text and then you force the model to do this, essentially what it tries to learn is, okay, given this context, I need to predict this word. So it means that somehow I have to align my representation of this WT with all these other context words WT. And in that process, what you'll get is similar representations for words that appear in similar context, right? So this is the idea of SIBO, right? Now a reverse. Now if you understand SIBO, now then a simple reverse idea is you have the target word WT. Why don't you try to predict the context words, right? So given WT, now the objective becomes probability of WT minus maximizing probability of these entire context given this word, right? Intuitively, you can think of this as a more stricter version of this, right? Because having a support of different words and predicting one single center word is easier than having a single center word and then predicting the entire distribution, right? So yeah, this is like a stricter version of this. Yeah, so am I clear with the idea up till this point?
Yes, sir. Sir, I have a question.
Yeah.
For this two component continuous bag of words and escape grams, so for word to vec, yeah, they contribute equally or they perform differently. For yes,
Okay. When you say contribute equally, what do you mean?
I mean the performance or the embeddings.
Yeah. So since this is a more stricter version, this tends to perform better, and people generally use this skipgram method, right? Because it is a more stricter version. But I think the performance of this is superior to this, right? Uh, but training this also has its challenges, and we'll see them. Uh, but yeah, I mean this has a better performance. Right? Is it clear?
Yes, sir.
And also, I mean, there is no objective. Uh, I mean, there is no objective answer to this because we have seen that for some languages, for English, let's say skipgram is performing better, but then there are different languages. When we deal with Indian languages and all, we see that sometimes SIBO is performing better. So, I mean, this is an empirical thing. You have to try both out and see which one gives a better representation. But yeah, I mean, intuitively, if you think about it, this is a more stricter version. So, more stricter version should sort of give you better understanding given a large enough data to sort of train this model. Okay. Fine. So, yeah, having understood the idea of this, what we can start looking at is how do we implement one of these, right? How do we implement one of these from the ground up and train this, and then see what representations are we getting for different words from a corpus. Okay. Okay. So now for training this particular setup or model, we will sort of download a data set from the TextAid data set. And basically, it's a Wikipedia article text. And then I've written all these steps where it will save your data into the data directory and everything. So we can just directly start running it. So it downloads the data from S3 from Amazon AWS. Right? So it's in a zip format. So we have to unzip it. Uh, Let us see what this text looks like. Right? The first 100 characters looks something like this. Doesn't make much sense. Maybe we can sort of look at last 500 characters, first 500 characters. So it talks about anarchism and English Revolution, radicals, and all sorts of things, right? So more of a history and philosophy related topic, right? Okay. So now we have our data ready. So then we will sort of do a pre-processing on this. When I say pre-processing, we'll sort of format the data in some form or the other. So what we are basically doing is, for stability of model learning, basically we are converting the entire data text into lowercase, right? And then we were replacing this dots and punctuations and all these symbols with their equivalent English uh, marker. So semicolon becomes actually what the word semicolon, right? So this helps in sort of stabilizing training, because sometimes you see, having certain special symbols and all, they do mess up with training. If you have a smaller model, for larger models, they do not matter much, but you have smaller models, they do mess up with the training. So it's always better to kind of normalize these things to a similar space where the other words are residing, right? Yeah, so this basically does that. Then we will sort of split the text on the basis of space, right? And we will get the individual words from the text, right? So, and then what we'll do once we have the individual words from the text, because the first thing that I showed you is you have to first create a vocabulary, right? During one hot encoding, also we were seeing that we had to first create a vocabulary. Vocabulary means a collection of words, right? So once we do that, then we can sort of think about that how we will represent these words into embeddings, right? So to create the vocabulary, first we need to extract the words from the text, right? That we did here. Uh, then what we do is we make a dictionary of the words, right? Based on their counts. So if you see, okay, to call it here. Right. So if you see, I printed this, right? Word counts. So word counts is basically a dictionary, right? And it gives me, okay, this word appears these many times in the text, right? This is just a key value pair of words and their counts. And why I did that is basically I want to trim certain words or remove certain words whose count is less than 5, right? Less than or equal to 5, maybe. So that is an individual choice. Uh, so because we are not very interested in rare words, right? We want, I mean, if a word appears once in a dictionary, I mean, okay, it's just for convenience, you can remove that word. So this is just a assumption, right? So there might be cases where those rare words are very important, right? In those situations, you might not want to remove them. So that is a very like task to task dependent setup. But yeah, so I hope you understand this part, right? Now you have the trimmed words, or words where 5 frequency is less than or equal to 5 is removed. Everything is in lowercase, and then you return these trimmed words, right? If you see, if I print the first 30 words, you see these words have come up. So now this becomes your pre-processed vocabulary, right? So once this vocabulary is ready, I think then we are sort of ready to build the embedding, right? Okay. Another another important thing and to do is basically create a dictionary. Okay, dictionary uh, which basically maps each words to its equivalent integer form, right? Because we will see that when we do batching or some sort of sampling from the data, we will not reference the word every time. We'll let's say, take this situation, right? You have 100 words, right? And you want to pick up 100 words. You want to pick up, let's say, 10 words from your 100 words, right? And that, which 10 words you'll pick comes from a probability distribution, or a random number generator, right? So my random number gives 3, 7, 6, 3, 4, 13, like this, right? So now if you don't have a conversion of your word to an integer, then you can't sample words from that, right? So for sampling words, you need to sort of have an indexing mechanism. So basically that is what we do here. Something called as, we create two function variables, which is like integer to vocab and vocab to integer, right? So what they basically do is, One approach does is you convert your vocabulary to integer, right? Each of the words have their own numbers or indexes, and then another is reverse, right? And that is needed when we sort of sample those words from the vocabulary, right? That we'll see a bit later. So let us see what does this basically gives us, right? Create lookup table. Let us first run this. Fine. Right, you get the words, and then maybe what we can do is, let us do v2i and I2v equals create lookup tables. What we can pass on is this words, right? Words we get from the after trimming and everything, right? And then maybe we can do print, let's see v2i, and then also print. Let us see v2i first, because this returns two things, right? So we all need to also capture two things. Yeah, so vocabulary to integer, what does it give me? It give me indexes of each number, and this is a serial indexing, right? So the appeared first, so the has 0 index, of appeared second, and so on and so forth, right? Also, let us see print. So I2v, this is a reverse mapping, right? 0 se the 1 se off, and so on, right? So these are mappings that we created here, and we'll sort of use them later. This is one statistics that we tried to see. What are the total words in the text, right? So total number of words in the text is this, and total unique words. So unique words would be something like 63,641, right? The rest everything is sort of repeated words, right? Okay, so creating these dictionaries, I already sort of showed that to you here. Let us not go into it. Now, there is another thing called as subsampling, right? So words like uh, the, of, right? Those words which are sort of they're referred to as filler words, right? They don't contribute to the meaning of a sentence much. So, for example, if you say uh, the boy is standing under the tree, right? So, if you have this sentence and if you remove the, does it have any impact on the meaning of the sentence? No, right? Uh, so words like these, they don't hold much semantic values. So maybe you can also discard them. And then this is from the original paper. So what they do is they sort of discard this with certain probability. I mean, this step is not very super important, but yeah, I mean, you can go through it if you want, right? Okay, so now, so basically here they do this particular sampling. So if a particular probability value is greater than this threshold, then only we will keep, otherwise we'll sort of drop them, right? So now let us see, after maybe dropping, what is the length of my vocabulary. Oh, sorry, train words is not defined. Anti words is not defined. Right? We see a lot of reduction, right? Earlier it was too much. Uh, where is it? You see, earlier this was this, right? But now you have removed words like this, the, of, right? And you see their contribution in the count. It's huge, right? So removing them sort of reduce the vocabulary size, that sense, right? Up till this point, is it clear? I hope everyone is following. I don't see any responses. So uh, if you're not following, just let me know. Maybe I can repeat some modules.
Hello, sir.
Yeah. Yes, Jayanta, go on.
Yes, sir, am I audible? Hello.
Yes, you're audible. Please go on.
Sir, these words we can remove by any pre-processing steps also. Stop words removal.
Yes, yes, yes. The stopwords removal you
So,
can do in the pre-processing step also.
so, so removing those, we no need to do unnecessary counting of those words.
Right.
Then remove.
So yeah. So nowadays, so this is basically this code is built up from the scratch, right? But in real life, when you sort of deal with this text and everything, so there is this library called NLTK, right? NLTK, and there are other certain libraries called Spacey and all. So they provide extremely good functionality, right? With a single line of code, you can remove the stop words and everything, right? So this is just for a demonstration purpose that, okay, these words exist, and you take any document, right? You will see that these. So Jayanta pointed out this nicely that these are called stop words. Sort of slipped my mind. So there's these stop words, the, of, is, and so on, right? If you see, you take any text, right? Any Wikipedia article, any books, right? And you see these stop words would contribute much more to the count in your vocabulary, right? So essentially, but they do not contribute as much to the meaning, right? So removing them sort of makes sense, but then you sort of constrict your vocabulary size, and then training becomes faster and so on. So yeah, I mean, here I showed you a lengthy step to do that, right? But in practice, one line would do from if you use those libraries, right? Okay, fine. So if you're okay with this, so let us now move on. And so now we have our vocabulary, right? Now we have our set of words, which we refer to as train words, right? So for just skimming through, what do our train words have? So now we see that our train words have all the indexes of the words, right? Uh, okay, I don't know what did it. But anyway, what I wanted to show is train words have all the indexes of the words that basically are in my vocabulary, right? So that is the idea of train words. Now we are not storing for data set creation purpose. We are not storing the individual words which are already pointed, because then it would be difficult for me to sample and make pairs and window it, right? So it is easier for me to handle it numerically. So for each word I have a unique ID. I'll use that ID to create my data set, right? When I say data set, what do I mean? If you remember skipgram, if you remember skipgram, what are we interested in? We are interested in this setup where given a word, you would predict its context words, right? So to enable the model to do that from your set of words, right, you need to first create this pair, right? Pair of what? Pair of WT and its context. And this window we will define, right? We'll define 5, let's say. So basically, around these words, what are the 5 words that I can take, right? Or what are the 4 words that I can take if I include this word, right? So we need to create this pair first for the model to train. We know that a model, when a model sort of goes into training, it takes in this entire takes in this two matrix, right? One is x and another is y. X is basically the input and y is the output, right? So you have the x, your model would predict something called as y hat, right? And then you have the ground truth as y, and then you would do some form of loss computation based on y and y hat, right? It can be MSE, right? Mean squared error, or MAE, mean absolute error, if it is a regression kind of a problem. If it is a classification kind of a problem, you can do cross entropy loss or binary cross entropy or whatever, right? But this is the problem setup, right? You have the input, you predict the output in this way. So for that, you need to prepare this pair also, right? So that is what we are going to do now. Right? So something like this, right? Let's say you have this vector, right? Say we have an input and we're interested in IDX2, which is token 741, right? So for r equals to 2, which is basically the history words, we'll take 2 from this side, 2 from this side, right? So now your context becomes, so now your x, so now your x becomes like this. Now your x is basically 741 and your y is basically this particular. So I hope you can sort of relate to how input and output works in neural networks, right? So to achieve this functionality, we define this method called get target, right? So you give in the set of words, you give in the index, which is your center word, and then which words you want to basically take out from its neighbor, right? This is what we are basically doing here. And if you see this, let us run this also. Okay. So this is just a testing purpose code that I wrote. Here, basically, you have, let's say, integer text. So now one thing to keep in mind, that now we are not dealing with words, right? We are dealing with the indices, right? So basically, given an index, so when I say 741, I can use the integer to vocabulary dictionary that I already created, right? So I'll input 741. I can easily look up what is the word in 741 index, right? Because now this becomes easy for me to deal with numbers, right? So that's why we created that dictionary mapping earlier, vocabulary to index and index to vocabulary, right? Fine. So now what we can do is, given this integer text, right, we want to see the input, right? Input is this. Basically, it's a simple code, right? You generate all the numbers up to 9, right? Range 10. And let's say your index is 5. This is your centered word. So when I call the get target function, right, with window size 5, right, what does it give me? So around 5, right? Around 5, these words I can get. 2, 3, 4, right? And 6, 7, 8. So let us also change the window size and see. Around 5, right? That is our target. 0, 1, 2, 3, 4, 6, 7, 8, 9. Let's say if I have something as 15. Right? So given this window, it would sort of sample out certain numbers from both sides. Okay. Let's say if I play around with the window size, let's say my window size is 1. Let's see. Right. So my target is 5. My window size is 1. So one number from here, another number from here. I hope you are able to understand this. So 2. So 2 number from here, 3, 4, 2 number from here, 6, 7. Right. So this is a sample code to sort of show you how this is working. Now we have this entire set of words, right? which we already know from this brain words, right? Now we need to create this similar thing for all the words, right? So for every word, you would sort of go to that word, you would sort of treat it as the center, and then you try to extract out words from its window, right? So that is what basically this code does. You see, for IDX in range 0 len words and then batch size, right? And we are stepping up with the batch size, right? If I want, let's say 30 words in a single batch, then this basically will take out the first 30 words and then create this particular mapping that we already saw, the generation of the word and its window. So if we kind of call this function get batches, right? And if we see what the first batch returns, right? So something like when the token is 0, when the centerpiece is 0, I'll get 1 2 3, because uh, before 0 there is nothing, right? And then if I give 1, what I'll get is one number before 1 is 0 and then 2 3, right? Some similar to this 3, then we get 0 1 2, right? So because ultimately you have only four words right here. So that is what you are basically seeing here, because batch size is 4, right? So this is how this entire mapping is being created between numbers, right? Now, if you sort of jump into the model, what you see is you have this input vector, right? And this input vector basically, this input vector basically is the input vector of WT, right? And then you have this one hidden layer neural network, right? So this is the architecture of skipgram. Basically, you have a one hidden layer neural network. So there would be a weight, there would be some weights here, there would be some weights here. The idea is this WT would come here, right? This would be compressed here in this neuron, in this sort of layer, and then you'll project back, right? And what you'll try to do, basically, this particular output's dimension would be equal to the vocabulary dimension. Let's say you have 30,000 words in your vocabulary. So this particular output would be 30,000 in dimension, right? So when we do probability distribution over this particular vocabulary, basically what you're trying to do and what we'll be trying to force the model to do is maximize the probability of those neurons which correspond to the context window words of that particular WT of this blue, right? Does it make sense? So you see here probability that the word chosen from within a context window is the. So this word, basically in your vocabulary, you have a set of words, right? And we know that each word is attached with an index also. So basically this zeroth would be mean the word that is in the zeroth index of that vocabulary, right? So we are trying to maximize the probability of the context window words. Let's say running 9, arts and chill, right? If these are my context window words. I hope this is clear. Any questions up to this point? Okay. So now this is a helper function that I've created. So basically what it does is during training of this model, right? During training of the skipgram model, we'll randomly pick up certain words from the vocabulary, and we will see which are the closest words uh, to that particular word, right? And how do we define the closeness metric? That is basically the cosine similarity, right? So ideally, we want that after training this model, once the model is trained entirely on the corpus, Wikipedia corpus that we already gave it, and sort of we created the data out of it. So we want that similar words would have similar representations. So cosine similarity between them should be close to 1, right? and dissimilar words should have cosine similarity close to 0, right? So that this basically picks up certain words from the vocabulary and then checks its embedding, right? Okay, one thing I think I missed is where do we get this embedding from, right? So let's say your model is trained and everything, right? Then let's say you want to find out, given a word X, I want to find out the embedding of X. Where would I find that embedding from, right? So that embedding is basically you get from this. After the model is trained, this weight matrix would serve as your embedding, right? So for example, uh, if this word basically is of, let's say, some d dimension, okay, so this would be down projected here, right? And then once this, you get the down projection here and all sorts of matrix computations here with multiplication with w and all, right? So you'll get the hidden layer here. Now from the hidden layer, right, you can get the output here. So basically this particular weight, right, its dimension would be of generally d cross vocabulary size. So given you take a word, uh, let's say w, when you pass through this network, then you can easily extract its and let's say that w resides in the index 536, right? So when you pass that word here, uh, and then you check this weight matrix, right, before you apply the softmax probability and everything, you check this weight matrix here. Now if you take that particular position's entry from this weight matrix, that basically gives you the word embedding of that particular word w that resides in 536 or whatever id or index that you're talking about, right? So once this model is trained, so now I'm talking about that this model is basically capable of sort of generating word embeddings, right? But where are the word embeddings? Because if you see the output is nothing but a probability distribution which maximizes that, okay, you have this word, what are the context words, right? And that is how your model is trained. But where do you get the word embeddings from, right? You get the word embeddings from this matrix, right? Okay, so okay, I covered this part. Now let us come define the skipgram class, right? So we'll create this neural network skipgram. And I hope you remember how to create neural networks from earlier lab sessions. So basically, you have two layers, right? What are the two layers? Basically, you have one hidden layer, but two weight matrices. So you would have some weights here, you would have some weights here. Let us see. So in your skipgram model, right, what you will do is you will create this self.embed layer, and it is basically an embedding layer. So what is an embedding layer? It is nothing but it has some weights, right? Just like we saw in linear and everything, linear layer and everything, right? So what does it take? It take n vocabulary times n embedding, right? Basically, you'll pass in the vocabulary, right? And then you'll get some embedding, right? And then this embedding, once you get this embedding, you'll pass it through a linear layer. So once you get this embedding here, you can pass it through a linear layer. That is a dimension embedding and vocab, right? Because in the output, we want to have the entire set of words because we want to maximize the softmax probability of certain words that appear in the context of the target word, right? So that is why in the output, you need to have the entire vocabulary. For each vocabulary position, when I say vocabulary position, right? If 500 is my vocabulary size, then 500 dimension output would be there, right? And then my aim is to maximize the position of those words, maximize the probability of those words that should appear ideally in the context of that given word, right? And that's why we do log softmax here to convert it into a probability distribution, right? And this is a simple forward function. You take the input, you pass it through them, and finally you get the log probability, right? So let us also start running it. I don't know up till which point I executed the code. Okay, this is done. right? Now our model is trained, and you remember our data is also ready, right? In the get batches method, you remember we were creating those pairs, X and Y pairs, right? Where X is the target word, Y is our context words, right? So that is basically what we're doing here, right? So we were iterating over those batches, right? And then this is just typecasting them into long tensor, because PyTorch wants this, at least I'm not sure about inputs, but targets is something that PyTorch always wants in long tensor form, right? Whatever is your target, but your final output, ground truth output, PyTorch always wants that in long tensor form. So I mean, I think you can also remove this, but yeah, just for sake of completion, I've written this. And then also because last lab, we remember, right? Your model, either it can be the CPU or in the GPU, right? If it is in the GPU, then your data would also need to be present in the GPU. Otherwise, your computation can't take place, right? So basically, since we are using GPU here, so we want to basically move our inputs to that device. So now the device is basically CUDA, if you remember, right? What we do is, from you call the model, you pass in the inputs, right? What is the input here? The input is those target words, like WT, right? And then you get some log probability, right? And then what you're trying to do is maximize. You're calling this loss function, right? What is this loss function? Can anyone tell what is this loss function? So basically, this is a NLL loss, which is nothing but log likelihood, negative log likelihood loss. This is equivalent to cross entropy, but the only thing is, if you call cross entropy, it will apply the softmax, and then it will do the cross entropy, right? But for negative, then it would do the this log likelihood. But for NLL loss, you have to manually first apply softmax, and then you can call it, right? So if you're not very clear with the loss function, you can check it, right? How do cross entropy loss works and everything. I'm not covering them now. So basically, in every classification kind of a problem, either you can use cross entropy loss. Classification means where you're given the input and then you have to classify which class it belongs to. So for those kind of purpose, you can either use NLL loss or cross entropy loss. Cross entropy loss does the softmax. For NLL loss, if you're using, you have to do the softmax yourself. You see, we did the softmax, log softmax here. But for cross entropy, it does it in the loss function itself, right? And then so let us see. Let us print what is the log PS and what is target here. You see, it's printing a set of numbers. So maybe we can stop it and then see. So what are you printing here? Is there something else also being printed? Let us. think there is some other things also getting printed, probably from somewhere up the code. I have to check, but yeah, what we were trying to see is how does the log probability look like, right? So this is basically nothing but a tensor, right? And this is a 2D tensor because you're doing it over a batch, right? But if you think of it as a single, single input and output setup, if you're not doing it over a batch, when I say batch, I mean multiple sort of training examples. So this would be a 1D vector, right? And this basically gives us the probability of the over the entire vocabulary, right? So this basically gives us a probability of over the entire vocabulary. And now we have done this, and we see our targets, right? So this is like you have this target here, uh, and we want to sort of maximize that. Okay, for this position you have this probability, for this position you have this probability, and you want to maximize this target. So these are like context words that should have appeared for that particular word, right? So this is how this training would take place. And just for clarity, I can sort of maybe put this out. And I also want to maybe remove some other print statements. I'm not sure where I defined them. Oh yes, I defined them here, right? So these were coming from here. Um, okay. Right. So it is training, and you can see after every steps, not after every step. I mean, after a certain number of steps have elapsed, what we are doing is basically printing randomly, taking out certain words from the dictionary, from the embeddings, and we are seeing that what are the closest words, right? So in this way, we can sort of understand, are the embeddings being learned correctly or not. So this is like you take a vector from your vocabulary, right? You take its embedding, you check its embedding, and check for all the words that are in the vocabulary, which are the closest words, right? For which word this vector, this particular words vector has highest cosine similarity, right? So that basically gives those words, right? So now if you see, at this point it's pretty bad, right? Because it's still training. But after a certain number of iterations, you'll see similar words getting sort of picked up. So let us see here. For example, prince, right? Prince, similar word to prince, forefather, ring, railroaders, doesn't make sense. For example, police, catastrophic, recoverable, doesn't make sense, right? So now this is pretty bad, but after few iterations, we can sort of clearly see the similar words getting placed nearby. So maybe what we can do is maybe we can wait for maybe 5 minutes. Let this run a bit. Let us see what is the result. Right. Meanwhile, you guys can also sort of try this and see. Maybe also if you have any questions at this point, maybe I can also take that.
Hello, sir.
Yes, Jayant, go on.
Sir, I need a suggestion from you related to multimodal search engine.
Yes, please.
Sir, to build a mini multimodal search engine, what are the things we'll require?
Uh, okay, so when you say multimodal, what modalities do you have? Image, text, audio, video, what is it?
Sir, image and text.
Okay, so if you have image and text together, then you would probably need the understanding of something called as multimodal embeddings. Multimodal embeddings can be computed from different models. One very popular model is CLIP, right? Um, so basically, CLIP takes in input as image and text and then gives you one single. Um, I mean, it gives you embeddings of image and text separately, but you can sort of with minor modifications, you can get a single embedding out of it. Now, once you have those embeddings, then you can sort of store them, their embeddings, right, in some vector DB or something. And then based on your query, you can sort of, I'm talking about a very naive approach, right? Based on your query, if you have a query that comes up, let's say if you have a multimodal query only, or it can be other way around, right? You can have uh, images and then you can query with text and see which images are more relevant to that piece of text. In that case, you need to take out the image embeddings and then store them in vector DB or something. And then once you have the text embedding, well, let's say the user gives you a query and then you take the embedding of that query, right? And then you take a cosine similarity between the text and image embeddings, right? And you basically retrieve those images corresponding to whose embeddings you get a higher cosine similarity score, right? That can be one simple approach. Uh, is it clear, Jayanta?
Sir, at the end, your voice got muted.
Okay. Up till which point could you hear?
Till, sir, vector DB
Yeah. So if your
for
requirement
embeddings.
is, yeah, if your requirement is something like given a text, I want to um, fetch an image, right? Or given an image, I want to fetch a text, right? So basically, you want that the embeddings of text and image uh, should be closer, right? So if you have an embedding of a text, let's say this is a cat, and then there is an image of a cat, then their both their embeddings should be closer in space. Now, since we are reading embeddings, it's a good question. So, so Clip is such a model, and there exists other models, but Clip is the most simple and more, I mean, very popularly used. What it does is for similar sentences and similar images, right? If I'm talking about cat and the image is also about cat, Clip tends to give embeddings which are very closer to each other, right? So if you take the text and image embeddings and you find out their cosine similarity, you'll see get a high cosine similarity, right? So that becomes an ideal model for us to kind of that becomes a very ideal model for us to use that. So now what you can do is if your objective is given a text, you want to retrieve an image, right? In that case, you can from your data set you can find out the embeddings of all the image and then you can store them somewhere, right? Now given a text, you can take the text embedding from clip itself, and then based on the cosine similarity of all the stored image embeddings, you take out the higher scored embeddings and you can sort of return those images, right?
Sir, for storing the embeddings, we can use Facebook AI similarity search.
Yeah, so that is an optimized thing, right? FICE is a very optimized. If you have very large dimensions, you can use FICE. But I'm talking about on a very simplistic level, right? So yeah, I mean there are other optimized techniques also to compute the cosine similarity. But yeah. Fine. Let us get back to our discussion. Uh, okay. So it has executed some iterations. Uh, yeah. So you see one similarity popping up is if you have this 8, the word 8, its vector representation is similar. Oh, where is it? Missed it. Its vector representation is similar to these numbers vector representation, right? And it makes intuitive sense because numbers should lie closer in space because those belong to one category, right? Similarly, if you see stage, right, words like theater, performances, actors, theater, film, they have come very close, right? So you see how this distributional semantics is being playing out. You see operating, you see Windows, Unix, OSCP, you see HTTP, closest words are www, HTML. Makes sense, right? Then some more, let us see. If you see police, right, closest words are officer, enforcement, military, criminal, robbery. So if you think about it, when you read something about police or something, these words tend to pop out more often than not, right? Similarly, women, right? Her, she, children, adult, women. So I mean, now you see what I was talking about, right? So, so if you see some more examples, you see construction. We have constructed, cement, demolished, projects, concrete. These words are very related to construction. You see Bible, biblical, testament, Christian, God. You see pressure, atmospheric, currents, pressures, contact. So like this, I hope you understand what is going on here, right? So similar words are tend to be getting closer. Recorded, album, records, live, right? Now, so this is one visualization code that I sort of prepared. Let us see. So let's see if it works if I close it up. Okay, so these are the vectors. Okay, so another thing to note here is, these vectors were high dimension vectors, right? What was their dimension? Let us see. These were 300 dimension embeddings, right? But 300 dimension is not possible to visualize. So there are some methods like PCA or TSNE. What they do is they basically compress your or they project your 300 dimension to some 2 dimension for you to visualize, right? So if you see, I hope you can see my pointer. So if you see words like play, players, they are coming close here. Played, right? But then these are very far off from words like Catholic, Roman. Then Roman, Catholic, these words are close, right? Similarly, something about computer, then software, systems, special, these are close, right? Then see a lot of close spaces here. This is not perfectly trained because I stopped the training in between, but if the training if I allow the training to get completed, then maybe you can see better clusters, right? You see months getting name of months getting nearby: February, March, June, January, right? July, April here, everything, August, November. You see names getting close by here. Similarly, prime minister, president, government, council, they are getting close by here. You see civil, battle, war, military getting close by here. So I mean, this is extremely nice, right? I hope you could understand what we were trying to do and what was the result that we were getting. So if you go up, you see high, low coming together. So one thing to be very cautious of when you explain this word similarity to someone, it's not that words which are synonymous to each other would only get higher scores, right? This principle that these models follow is something as distributional semantics, right? So words not necessarily if they're synonymous would come close, but words that appear in similar contexts, right? They should come close. Right. Is there any question up till this point? Okay. So now there is a problem. I mean, this method is fine, right? Everything is fine. We can see the results coming up, similar words being grouped together, and all that. So that is all fine. But then we have to sort of keep this in mind that this was trained on a very small piece of text, right? But in reality, if you really want to get uh, good clusters of words, right? You really want more similar words to be coming together and everything, then you would need to train it on a very large piece of text, maybe hundreds and hundreds of documents, right? And one thing during training was what we were doing is basically, so this is the softmax function that I've written here. What we were basically doing was, we were calculating softmax over the entire probability distribution, right? Now, suppose your vocabulary size is very large. If you take a lot of documents, obviously your vocabulary size would be very large, right? Then computing this term, this denominator term over all the vocabulary words, it becomes very expensive, right? For our case, we did not feel that because the data was small, but ultimately it becomes very expensive, right? So what people thought of is, can we do some proxy method to sort of compute this sigma zi, right? And what was that proxy? That's basically called negative sampling. So what is the idea of negative sampling? Is basically uh, so if you intuitively understand this, let us first intuitively understand this. What does it mean? So it basically says, given my, and we are talking about skipgram, right? For simplicity, let us talk about SIBO. What does SIBO say? You want to maximize the probability of WT given all the context words, WT minus 2, T minus 1, T plus 1, T plus 2, right? So I'm taking, although we were dealing with skipgram here, but for this, for me to make you understand this formula intuitively, let us think of SIBO. It would be easier. So now, given this context, WT minus 2 up till WT plus 1, right? What my model was doing was maximizing this E term, right? So given this context, it is maximizing this term with that context while minimizing other words with respect to that context, right? So basically, it's like, given this context, and if you visualize these context words in the space here, right? So these context words would lie somewhere near, and then I want to push my target word closer to that context word while pulling away all the other words, right? And these other words would come from some other words in the sentence, right? Not from the similar, not from that same sentence, right? These other words that I was talking about would come from some other words in some other sentences, not from that sentence that we're dealing with here. So essentially, it's pushing the similar words together and pulling away the dissimilar words. Essentially, that is what this particular function achieves, right? So what these people did was to achieve a proxy. What they did was to take. So first challenge with this is you have a lot of words in the vocabulary, right? And when you do this computation over the entire vocabulary, if you have a very large vocabulary, millions of words, let's say, and doing this computation is extremely heavy. So to get away with this computation, what you need to do is somewhere you should think that you do not need all the words in the vocabulary, maybe with few words. And when you talk about this denominator, these are basically words that do not appear in the context of the sentence that we are dealing with, right? So if we are dealing with the sentence, I am learning artificial intelligence. Here we are predicting, let's say, artificial, but all the other words in my sentence that's not in the sentence, all the other words in my document that's not in the sentence, I love artificial intelligence, would come here, right? So basically, can we sample rather than treating all the words or considering all the words from my corpus, can we sample certain words and then achieve a similar effect, right? So what basically this term says that, so this is the negative sampling loss function. What they do is, given your input word, embedding of input word, you maximize the similarity with the embedding of the output word, right? So the sigma is the probability, and we do log probability because when we sort of iterate over batches, the probability becomes small. Then there is this numerical instability problem. So log would sort of, multiplication of probabilities means log would add up those probabilities, right? So that is important. So given this input context, wt minus 1, t minus 2, and so on, you predict the output wt, you maximize that score, right? And what you minimize upon? You minimize the noisy target. You take samples randomly, some words which are not in that sentence that we are talking about, and then you try to sort of minimize their similarity. That's why this minus is here. So ideally, if you're dealing with correct target and everything, so this similarity would be 1, right? And this would tend, ideally you would want this to be very close to 0, right? So now you see you are saved from this operation. Now you can basically pick out certain random words, right? Basically, so this term basically says expectation, right? So expectation from certain random words. You take, let's say, 5, 10, 20 randomly words which are not related to the target word that you're talking about, and then you try to increase their dissimilarity. So you see the first term in the loss pushes the probability that our network will predict the correct word W0 towards 1. In the second term, since we are negating the sigmoid input, we are pushing the probability of the noise towards 0. So it's like this term basically increasing your probability, this term basically increasing your probability to the correct target word, this term basically decreasing your probability with the noisy target words, right? Is there any question considering this function? Okay. So this is clear. Here, what we are doing is basically implementing this particular setup, right? So this is skipgram neg, which means skipgram with the negative sampling. Earlier we saw skipgram had n vocab and n embed because those are the layers that we were talking about. So these are input embedding layers that we create. We are sort of defining. So I was talking about this embedding layer, right? These are simple weight matrices. So what here, for better convergence, what we are doing is basically sampling the weights from a random, uniform random distribution, right? And this is how our input vector would propagate. This is how our output vector would propagate. and this is where we are creating the noise. What we are basically doing is from the vocabulary, and that is why I was talking about this words being converted to numbers, why it is important for us to have index attached to every word, and it's easier to deal with indexes because now we want to randomly sample words from the negative set, right? So negative set is basically all the sentence, all the words from the sentence for which I'm not considering this, right? Let's say my sentence is I love artificial intelligence. This is my target sentence. From here, I'm creating those pairs, right? WT, WT minus one, and all that. So excluding this sentence, all the other sentences that's in my corpus, the words from those sentences would be my negatives, right? Now, earlier, before we were doing softmax, before we were doing negative sampling, we were picking all the negative words, right? But we saw that is computationally inefficient. So now what we'll do is randomly sample certain words from that negative set. How? You create a noise distribution. So noise distribution is nothing but what type of distribution we want. Either you can have a torch.1. So basically this is like uniform distribution, right? Or I think I have defined some distribution here. Okay. So let us consider this is a uniform distribution, that uniformly you can pick up any word, right? Probability picking up any negative word is equiprobable. So you pass this vector to this multinomial distribution, right? You want to sample how many samples here. So this is like for each batch size is, let's say 10, right? So you have 10 training examples in one batch. So for each training example, you would pick up some n samples, right? So that is why this vector is created here, noise words, right? And then you will basically pass these noise vectors through the embedding and all that we did, right? Matching the dimensions. So this is not very important. I mean, you can run those and see what are the dimensions and all. Now, this is the skipgram neg class, right? Now we also created a class which basically caters this loss function, this one. So what this basically does is you have the input vectors, right? Input vectors would be something like here input vector would be WT. If I'm talking about skipgram, your input vector would be WT, right? What would be your output vectors? Your output vectors would be like one large probability distribution over the entire vocabulary, right? Because that is what your model would output. That would be your output. And then, so this is your input and output. So basically, now we are talking about this term. So input and output, right? Given this input, I want to maximize the probability with the target output. So this sort of happens here, torch.vml. And then you take the sigmoid and log and everything, right? For the noise, you have the noise vectors, okay? So you pass in the noise vectors here. So we'll see where from we are creating these noise vectors. So you have the noise vectors and you sort of multiply them with the input vectors. You take the sigmoid. Basically, you want to reduce them, right? And then you squeeze. So you're reducing dimension and you're doing the sum. So basically, let's say your input text is one word and these are 10 words, right? So you do that repeatedly and then you would sum up, right? Then finally, what you'll do is negative of out loss plus noise loss. So this is out loss, this is noise loss. You do the negative, right? So it's like if you take a bracket here, this would be positive. So you do the entire negative of this entire thing. And obviously, because now loss should be a single scalar value, right? So you do the mean over all the batch, over all the training samples, right? And then sort of you'll achieve the same thing, just that it's now more efficient, right? Does anyone have any question on this loss metric and how it is different from your earlier loss metric that we were using? And this is the most crucial part. I mean, the takeaway of entire negative sampling is this only. So I'll wait for a couple of minutes. Okay, I'll just quickly once again go to this loss and maybe tell you the distinguishing factor between these two. So it's like uh, you have if I'm talking about SIBO, right? You have the context, right? And in the output, you would predict the WT. You have WT minus 1, say WT plus T minus 2, say WT plus 2, let's say. And you want to uh, output WT. So basically, you would want to increase the probability with the context of this word. This is a conditional probability, right? You have those words. Now your neural network based on those words is giving you this output. But at the same time, you want this output or this word to be very different from all other words which are not in that sentence, right? Which are not in the sentence. If I talk about the sentence, I love artificial intelligence. So that's why you have to consider all the words in the vocabulary, excluding that sentence, right? Now that becomes very expensive, right? So what this particular loss function tells us, you need not do that. What you can simply do is you maximize the similarity, right? Earlier, what you are doing is given the input word, you maximize the similarity with the output word, right? This is the embedding of the input word. This is the embedding of the output word. Now, instead of the denominator, where you are doing this sigma e to the power zj computation over all the words in the vocabulary, all the negative words in the vocabulary. When I say negative words, I mean words that are not in that sentence, right? I love artificial intelligence. So instead of doing that, from the negative set, you pick up certain words, right? You sample certain words, and then you minimize their probability, right? So basically, you minimize their probability. That's why you apply negative here. Sigma of negative means their probability would be reduced now. So with those words, you minimize your probability of the target word WT. And these are embeddings, right? These are embeddings of those words. You and we are embeddings of those words, right? Now you see, so the same push-pull effect is being played out here. In the space, you're maximizing the similarity with the correct words, and you're distancing them from the non-correct or negative words, right? So that same push-pull effect is being sort of captured here, right? And then with this also we saw the implementation of how to do that. So the brevity of time, I will not run this code. Maybe you can do it yourself. But yeah, ultimately this is the idea. The only change is this, and for simplicity, we created another class where this loss function is being computed, because this is the sort of crux of this particular method, right? So this particular method is called word to vec, right? So what did we cover? We cover something called as one-hot encoding. We saw the problems with one-hot encoding. One is sparsity, one is fixed nature. Your new words cannot be encoded here. And then it sort of scales with the vocabulary size. If your vocabulary size becomes 50,000, your embedding size would also be 50,000, right? But here we saw that our embedding size only depends upon this dimension. Only depends upon this dimension, right? If you want 300, then this dimension should be 300. If you want 400 dimension, then this is 400. So for if new words come to the vocabulary, our dimension of the vectors wouldn't change. And then another was semantics, right? So there was no semantic meaning between man and women. That inherent nature of semantics was not being captured. That's why we talked about word to vec. Now within word to vec was a neural approach. Within word to vec, there were two approaches: SIBO and skipgram. We discussed SIBO and skipgram. SIBO is you have the context words, you predict the center word. Skipgram is you have the center word where you predict the context words, right? And we saw how to do that. Then the problem with simple naive skipgram or SIBO is you have to compute this uh, exponent term over all the negative words in your vocabulary, right? So to mitigate this, we came up with this, right? Where you get the same push-pull effect, but in a different way, where you can simply sample certain words, negative words, and reduce their probability, right? So that this works as an approximation, right? And then we saw the code here. So this is one technique called word to vec. Then there are other methods like fast text, glove. So these are non-contextual embeddings. We'll look at the next lab session. What do you mean by contextual embedding? What do you mean by non-contextual embedding, right? Uh, so so there are now two problems with word to vec also. So let us say if you get a word that is not in your vocabulary, right? So I already said, right? This is your, if I can show you the, yeah. So this dimension is basically your vocabulary times embedding size, right? And this is your embedding size times vocabulary, right? So you get, uh, so let's say you're taking this weight matrix. So let's say I tell you to extract out the word vector of a word, let's say man. How will you do it? So you'll go to this place or this place, right? And you'll find out the index of the word man, right? And you will take the corresponding vector from this weight matrix, right? In a transpose way, you can also do it, right? Because this is vocabulary cross embedding. This is embedding cross vocabulary. So this is like a transpose of this. You can also take it from here, right? Now, the problem is what happens if you do not have certain words in your vocabulary. Let's say your vocabulary initially when you trained the what to vec model, your vocabulary didn't have the word, let's say some word as parachute. Right? What do you do then? Or a better example would be, let's say you trained on a corpus where you had the word love, right? But then a new word lovingly comes up. But you know that love and lovingly essentially they mean the same. On a surface level, they mean the same, right? So what do you do? So to tackle this problem, what fast text does is, instead of treating each word as one single word, instead of treating each word as a single component, right? What they do is they tend to break up words, right? So something like, if you have lovingly in your corpus, what they would do is they would separate it into two components: love and love ingly. So now they're trained for everything. Now let's say in your vocabulary, if you have trained for some words such as uh, joke, right, and a new word jokingly comes up. So now you have components, right? You have joke because you've already trained for joke. You have ingly. Those components also trained because that you did when you are doing lovingly. So instead of treating one word as a single component, they would break up each word into multiple pieces and then train on those, right? So idea is very interesting. So in this way, fast text kind of overcomes the vocabulary out of vocabulary problem, right? If you have a new word that's not in the vocabulary on which word to vec has been trained on, then what do you do, right? So something like this. Uh, but then these are called non-contextual embeddings because uh, consider this example. Uh, I deposited money in a bank, right? And another example, I was walking by the river bank. So you see, bank appears in both the sentences, but their meaning changes entirely, right? One bank talks about financial bank, another bank talks about your river bank, right? So ideally, if you think about it, their representation should be different, right? But what to vec and what to vec and fast text and globe and all these methods would give you is the same representation, which is not correct, right? So how do you deal with that? So for that, we have something called as contextual embeddings. So that we will see when we cover transformers and BERT and everything. So from there, we will sort of learn this concept, right? So yeah, I mean, these are very interesting things. You can sort of go and play around with this notebook, and yeah, let's meet on the next session where probably we'll cover transformers and everything. So yeah, any questions? Okay, if you have no questions, I think it's already time. So thank you guys for joining. So bye bye. Yes, Alice, you can end the session. Am I audible, Shifali? Anyone can confirm?
Yes, yes.
Okay. Okay. So we can wrap it up here. Thank you for joining. Silas, you can end the session if you're out.